If you happen to have missed it, this is the second video related to this function, and we're now going to evaluate a particular type of derivative of this multivariable function, the limit as delta x approaches 0, where it looks a lot like our definition of derivative from Calculus 1, but we have other terms in our function that were not in Calculus 1. So we're going to evaluate this. Turns out common algebra tricks may be used to clean up the mess, and then we'll see what we can determine afterwards from what we've discovered. So here we go. Limit delta x approaches 0. Every term that has x in it is going to get replaced with x plus delta x. 5y squared minus, so this is going to be x plus delta x and x plus delta x minus the original function x cubed plus 2x squared y plus 5y squared divided by delta x, and it's the limit as delta x approaches 0. So let's see what happens. I'm going to evaluate this rather quickly, this particular multiplication, because we've got a problem to solve here. But there are a number of techniques. One is called the binomial theorem. It can be multiplied out by hand, 3 separate multiplications. You can use something called Pascal's triangle to quickly generate coefficients in terms. All of those things are just algebra manipulation from much earlier courses. Otherwise, I would slow down right now. We have here x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2y times, I'm going to distribute it later because of the extra term over here, x squared plus 2x delta x plus delta x squared plus 5y squared. Now let's see if I can get it to fit on the paper. Minus x cubed minus 2x squared y minus 5y squared divided by delta x. And when you're writing that quickly, even if you're very confident, it is usually beneficial to pause and just step back and look for things. I'm expecting some behavior like a derivative in Calc 1 of a polynomial function. So I'm kind of hoping some of these terms will be gone, like the x cubed minus x cubed, the 2x squared y minus 2x squared y, and the 5y squared and the 5y squared. They're all going to be gone. What's remaining is 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 times 2 is 4 x delta x y, and this times this, plus 2 delta x squared y all over delta x. And I step back again and I look at it and I realize every term has delta x in it. I can factor and reduce. And this would become 3x squared plus 3x delta x. Delta x squared is added in there. 4x y plus 2 delta xy. Every term had a delta x. I reduced by 1. This is what's left. These terms become 0 because delta x approaches 0. I am no longer dividing by 0. That term has been reduced. And what's remaining is 3x squared plus 4xy. So this function we started with, we've taken a type of limit and reduced it to 3x squared plus 4xy. I wonder if there's something to be discovered here. But I've got so much algebra in between, I'm kind of going algebra blind. So let me see if I can't compile the information in a little bit more organized fashion for us. Now, pay attention here. This discovery is going to become the single most used tool for the entire remaining part of this course. I don't believe it's going to be difficult if you were able to effectively do some things in calculus in the first year, but it's really easy to get yourself alphabetically challenged, we'll find out here. So let's do a little switch over of papers. What do we have? So we have this function, and we have the limit we just calculated, which was 3x squared plus 4xy. And this limit had something to do with x. And in the previous video segment, we did something similar, but we were working with the y variable. And in that segment, we got 2x squared plus 10y. So if x is our variable that we're working with here, so notice we're not using both variables, we just chose to use one. When x was our variable, this polynomial turned into 3x squared plus 4xy. But when y was the variable, I've got 2x squared plus 10y. I am really trying to avoid pointing directly to matching or corresponding terms. But I do want to tell you what this is called. What we're calculating here is a partial derivative. There's a reason it looks like the definition of a derivative, and I hope it's sort of obvious why they call it a partial derivative. We only did one of the variables each time. So it's a partial derivative with respect to, and then it was either x or it was y that we chose to do. Now, there's a notation for this before we wrap it up. I'm falling just a little bit short of indicating a specific, we'll call it shortcut or rule for this derivative. Rule is probably the wrong term. Rules, more than one, is probably the proper term. But there is a notation. The partial derivative does not use the standard notation for derivative. It uses a strange little symbol that looks a lot like, well, it doesn't look like any symbol that we've used. It's not a letter from the Greek alphabet. It's not the number 2. Its closest resemblance is to a letter D from somebody's hand-scripted writing. And this would be the partial derivative with respect to x. And this one here would be the partial derivative with respect to y. It's the formal notation for partial derivative. It can be written differently. The partial with respect to x can be named with a subscript x, and the partial with respect to y may be named with a subscript y. This will become my more common notation, but I'll also go back to the formal occasionally. What we don't get to use anymore is the prime notation. The prime notation, that won't be used anymore. It's going to be one of these notations. That is where we're headed. The partial derivative, which will have many, many uses. You will find out as we move along. Stay tuned until then.